Ever notice how some things just work, even if you don't know why?
Oh,
Like
yeah.
turning your phone off and on again to fix it?
Right.
Physicists have something kind of similar with quantum mechanics.
Mm.
It's this insanely successful theory.
Yeah.
I mean, lasers, modern chemistry, the Higgs boson.
Uh-huh.
It even explains why matter doesn't just collapse,
Yeah.
but the WHY is still debated a whole century later.
That's true. We're great at using it,
Right.
but the deeper meaning,
Yeah.
it's still kind of elusive.
And that's what we're diving into today.
All right.
If you're into those big questions about reality,
Yeah,
this is for you.
I like it.
We're going way beyond textbook basics of quantum mechanics
Okay.
using this article for its 100th anniversary.
Nice.
The goal is not just to learn what it says,
Uh-huh.
but to really grasp the challenges
Right.
in figuring out what it all means.
I like that.
It's like having this powerful tool,
Mhm.
but the instruction manual,
Yeah.
it's written in some language. We're still
Yeah.
trying to decipher.
Definitely.
So rewind to 1925.
Okay.
Before that, physics was pretty much clockwork. You know,
Like a clock.
yeah, the starting conditions.
Yes.
You can predict the future.
Right.
Then, bam, quantum mechanics drops.
Uh-huh.
Total game changer.
Absolutely. And suddenly the act of measurement
Mm.
becomes super central to the theory.
Okay.
And that's where things get really interesting.
Because the old physics measurement was just like,
Yeah.
well, measuring.
It was just
No
measuring.
big deal.
Exactly right. You measure like a ball's speed.
Right.
It doesn't change the ball.
Makes sense.
But in quantum mechanics,
Yeah.
observing something
Mm.
seems to actually change the reality you're observing.
Whoa.
Like take an electron, for example.
Okay.
It doesn't actually have a definite position
Well,
until you measure it.
So before we look,
Yeah.
the electron's just kind of like
Kind of just hanging out.
nowhere in particular.
Nowhere in particular.
That's so wild.
This is where the wave function comes in.
All right. And it's important to remember it's not the electron itself.
Gotcha.
It's more like a way to calculate the probability of finding it in different places.
So like built-in randomness from the start.
Yeah, in a way.
No wonder Einstein was skeptical.
Right. But if the wave function isn't the electron,
Yeah.
what is it?
Exactly.
That is the million-dollar question.
No, man.
It's describing the electron's potential, all its possible states.
I see.
And this is where Heisenberg's uncertainty principle comes in.
Okay.
You can't know both the electron's position and its momentum
Yeah.
with perfect accuracy.
Hmm.
And it's not just because our tools are bad.
Right.
It's that those values aren't simultaneously defined
At the quantum level.
at that quantum level.
It's like trying to photograph a hummingbird.
Oh, I like that.
It's so fast, right?
Uh-huh.
So the picture's either blurry because
Yeah.
it's moving,
Right.
or it's sharp, but then we don't know where it went.
Exactly. We can't have both.
Yeah. Precisely. And this uncertainty, it's not just about our limits.
Right.
It's about the fundamental nature of reality
At that scale.
at that scale. And Einstein,
Yeah.
he was a big believer
Hmm.
that our physics should describe something real, not just probabilities.
Like there's something concrete out there.
Exactly.
He thought we were missing part of the puzzle.
I think he did. Which leads us to the EPR paradox.
Oh, yeah.
Yes, Einstein and his colleagues,
Uh-huh.
they came up with this thought experiment
Okay.
to challenge the very foundations of quantum mechanics.
Oh.
And it all revolves around this wild concept called entanglement.
Entanglement.
Yeah.
Yeah.
But to unpack that,
Mhm.
we'll need to pick up in part 2 of our deep dive. Welcome back to our deep dive.
Last time we were talking about how Einstein
Yeah.
felt like quantum mechanics was a bit too much like rolling the dice.
Yeah, too random, right?
Exactly. He really believed in a world
Uh-huh.
where things only affect what's nearby. You know,
Locality?
no spooky action at a distance.
Exactly.
And that our theory should reflect something real out there.
Not just math tricks.
Right. Not just probabilities and stuff.
He wanted something more concrete.
But then entanglement kind of messes that up.
It really does.
Because it's like these two particles are linked. Even if they're light years apart,
Yeah, it's wild, isn't it?
you measure one and instantly you know something about the other one,
Right.
even though no signal could have traveled that fast.
Exactly as if they're part of one system,
Yeah.
no matter how far apart they are.
But we can't use this for like faster than light communication,
Right?
right? Even though at first it seems like we could.
It does seem that way.
So why not?
Well, there's a thing called the no communication theorem. It's a bit complicated, but basically the measurement results on your end, they're random.
Okay.
It's only when you compare them to what someone else measured on the other entangled particle that you see the correlation. Oh, so there's no way to actually send like a prearranged message faster than light.
So it's spooky.
Yeah.
But not that spooky.
Not that spooky.
But it still messes with how we think about space and time.
Oh, absolutely. If those particles are connected beyond distance, what does that mean for the fabric of reality?
All right, my brain hurts a bit.
Yeah.
Let's go back to that wave function.
Okay.
If it's not the electron, but just the probability of finding it, then what's really going on?
Yeah, that is the million-dollar philosophical question at the heart of quantum mechanics.
It's like we've got this amazing map.
Yeah.
But we're arguing whether the map is the territory?
Right.
Or just a representation.
Exactly.
So Einstein and those like him?
Yeah.
They say there's some deeper reality that we just haven't figured out yet.
Some hidden variables.
Right. And the wave function is just standing in for now.
Exactly.
Like there's a secret code that would tell us for sure where the electron is. We just don't have the key.
We don't have the key yet.
Then you've got the Copenhagen interpretation.
Right. The classic.
Yeah. They're more like, hey, if it works, it works.
Yeah. They're more pragmatic.
Focus on what you can measure. Wave function's just a tool.
Just a tool.
Don't worry about what it really means.
Right.
So one side's searching for ultimate truth. The other's like, just use the tool.
Yeah, the pragmatists.
But are there any other ways to look at this whole wave function mystery? I mean, there are.
There are a lot of interpretations out there, each with its own take on the wave function and reality.
Like QBism.
Oh, yeah, QBism.
It always sounded kind of like a sci-fi cult.
In a good way, though, right?
Yeah, in a good way.
QBism or quantum Bayesianism.
Right.
It takes a pretty radical approach.
Okay.
It says the wave function isn't about objective reality out there, but about the observer's knowledge, their beliefs about the system.
So there's not the electron that's fuzzy. It's an IRR understanding that's fuzzy.
In a way, yes, QBism really emphasizes how our actions as observers influence what we see in the quantum world.
Well, it's very subjective.
Very subjective.
Okay, so we've got the hidden reality folks.
Yeah.
We've got the pragmatists.
Right.
And now the subjective folks. Is anyone close to the right answer about this wave function thing?
That's the wild part. All of these interpretations, they agree with the experimental predictions of quantum mechanics.
Oh, wow.
They just offer different ways of thinking about what's going on underneath it all.
So no clear winner yet.
Not yet.
Still deep in the mystery, even after 100 years.
It's true.
That's kind of exciting, though.
It is.
It means there's so much more to explore.
Exactly. And in the final part of our deep dive,
Okay.
we'll look at what these different interpretations mean for our understanding of the universe as a whole.
Welcome back to our final part of this quantum mechanics deep dive.
It's been quite a journey.
It really has. We've gone from, like, entanglement being super weird to these philosophical debates about what the wave function even
It's like we've peeked behind the curtain of reality and found out things get really strange down there.
So strange. And that weirdness, it's not just for tiny particles, right?
Nope.
It's got implications for, like, the entire universe.
Exactly. The whole shebang.
Okay, now we're getting really big picture here.
Yeah.
There's that whole field of quantum cosmology. What's that all about?
So basically, it's trying to apply quantum mechanics to the universe itself.
Okay.
Like its birth, its evolution, maybe even its ultimate fate.
So instead of like electrons and photons,
Yeah.
we're talking galaxies and black holes.
Right.
All quantumly.
You got it. And that leads to some pretty wild ideas.
Like a...
Well, some physicists think the universe itself
Yeah.
might be one giant quantum system
Okay.
described by a wave function that includes all possible states of the cosmos.
Hold on. So our universe is just one possibility
Yeah,
out of many.
potentially.
Like a cosmic choose-your-own-adventure.
Yeah, with infinite pages.
Whoa. Okay, so maybe there's a universe
Yeah,
where I did eat that last pizza slice
it's possible.
instead of being all polite.
There's a universe for everything.
But this is where things get even more complex, right?
Yeah, because quantum cosmology, it's trying to marry quantum mechanics
Okay.
with Einstein's theory of general relativity.
Right. The one about gravity.
Exactly. And that's proven to be a really tough problem.
Because gravity is all about how space-time bends. And quantum mechanics is all about fuzziness and probability.
Right. Those two don't exactly play nice together.
Not yet, at least.
Nope. That quest to unify them.
Yeah.
That's what quantum gravity research is all about.
And it's not just about, like, black holes and the Big Bang.
No.
It's about the very nature of time itself. Because in, like, classical physics, time is just this steady tick-tock.
Right, a constant flow.
But in the quantum world, things get a little weirder.
Way weirder, some physicists believe.
Okay.
That at the most fundamental level, time might not even be a fundamental concept.
Okay.
It could be that our experience of time is emergent.
Okay.
Arising from how quantum systems interact.
So instead of time flowing from past to present to future, it's more like time is a side effect of all this quantum stuff happening.
That's one way to think about it. It's a radical idea.
It really is.
But it's being explored by some serious physicists.
It challenges everything we thought we knew about reality.
It does.
My head is definitely spinning.
Yeah.
So after 100 years, quantum mechanics isn't just about tiny particles anymore.
No, it's much bigger than that.
It's about the entire universe, the fabric of reality, even the concept of time.
Exactly. It's mind-blowing.
And the best part,
what's that?
We're only just getting started.
We are. There's still so much to discover.
It's like we've opened this door to a whole new understanding.
Yeah.
And we're just beginning to explore it.
There are so many mysteries left to unravel.
Exactly. And who knows, maybe one of our listeners will be the one
to
make the next breakthrough, to finally crack the code of quantum mechanics.
To uncover its deepest secrets.
So if you're feeling inspired by our quantum journey today, don't be afraid to dive in and explore.
Keep asking those big questions.
And if you enjoyed this deep dive, don't forget to like and subscribe for more mind-bending explorations.
We'll see you next time.
Thanks for listening.